Hello and welcome to problem set 16. Our problems today will be from the topic An Introduction to Organic Chemistry and Nomenclature of Hydrocarbons. Before we get started, just a quick reminder that the worksheet to accompany this problem set is available online through my website. And with that said, let's get started with number one. Number one. Draw expanded structures, condensed structures, and line structures for the following. And there's an A through E. So I went ahead and made three columns. One is where we'll draw the expanded structure, one for the condensed, and the final for our line structures. A is butane. I'll write an A here. Bute means 4 carbons. The ANE ending tells you it's an alkane. So all carbon-carbon single bonds. So for our expanded structure, 1, 2, 3, and 4. And go back and saturate all your carbons with hydrogen. So that's going to be 3 hydrogen on your terminal and only 2 for the interior carbons. So I'm going to go ahead and draw in all of my hydrogen here, though it's a little tedious to do so. That is a proper expanded structure. Okay, condensed. We're not going to show any of these single bonds in our condensed structure. So we're just going to write CH3 for this terminal carbon, followed by a CH2 and another CH2. And finally, a CH3 for the last terminal carbon. Line structure is the quickest and easiest. Once you get the hang of doing line structures, you're going to want to draw everything in line structure. So put your pencil down. That's 1 carbon. That's 2, that's 3, and that's 4. And remember that in your line structure, you're trying to show roughly the appropriate molecular geometry. So each of these carbons would have a tetrahedral geometry. So these bond angles are supposed to show roughly 109.5. Okay, so just don't do anything where you're showing a really small, tight bond angle like that. Okay. B is cis-2-pentene. Pent is 5. The ENE ending tells you it's an alkene. Where is the double bond? The number 2 tells you it is off of the second carbon, so between the second and third carbon of that 5-carbon chain. Remember that the cis tells you something about the 3-dimensional shape. It is a cis geometry about the carbon-carbon double bond rather than a trans geometry. So for my expanded structure, since I really want to show that cis geometry, I'm going to go ahead and do it in the expanded structure. Remember that cis means that your largest 2 groups are going to be on the same side of the double bond. So I'm going to go ahead and show that cis geometry here between the second and third carbon. So this carbon, the CH3, it's got 3 hydrogens on it, is larger than the other substituent on that carbon, which is just a hydrogen. And this CH2, CH3, is larger than the other substituent, which is, again, just a hydrogen off of that carbon-carbon double bond. So my cis geometry has those 2 largest substituents on the same side of the carbon-carbon double bond. So I'm going to go ahead and write in all of my hydrogen. Again, it is tedious, but it is the proper way to draw these expanded structures. Okay, so there's my cis-2-pentene in an expanded structure. Now in the condensed structure, I don't need to show all of my single bonds, but I do need to show my double bond. Okay, and then off of that, since I want to show the cis geometry, I'm going to go ahead and put my 2 other single bonds to those carbons of the carbon-carbon double bond. And then I'll just condense this. I'll write CH3, and this is a hydrogen. and then this is a CH2, CH3, CH2, CH3, and then this is just a hydrogen. So a little bit faster than the whole expanded structure. Line structure is the easiest. Just watch out for that cis shape that you're trying to show. So put your pencil down. That's 1 carbon. That's 2. This is 3, and it's going to be a double bond between 2 and 3. So I'm going to go ahead and put that in. And then where you go from here, because it's cis, you go down for 4 and 5. Don't go up, because that would be showing the trans geometry. So not a bad idea to just double check. 1, 2, 3, 4, 5. 5 carbons. Double bond is at the 1, 2, the second position, and the cis geometry is being shown. All right, C. 2-methylhexane. Hex is 6. It's an alkane. We know this because of the A-N-E ending, but there's going to be a 1 carbon branch off of the second position. We know this because it is a 2-methyl for the branch group. So hex, 6 carbons. 1, 2, 3, 4, 5, and 6. All single bonds between them. And then at the 2 position, that 1 carbon branch, you can write it up or you can write it down. I'm just going to go down. And then an alkane, so we're going to saturate everything with hydrogen. So 3 on these terminal carbons, only 1 here to complete your octet, 2 here, 2 here, 2 here, and 3 here. And I hope you don't mind if I go ahead and leave off my hydrogen, because again, it gets kind of tedious when you're drawing in this many hydrogen in your expanded structure. All right, so condensed. For my condensed structure, I'm not going to show any of the single bonds except for the branch group. So I'm going to do a CH3 for this first carbon, followed by a CH. Make sure you understand that that's just a CH. Only 1 hydrogen there to complete the octet. But there is a branch group. I'm going to draw my line to my CH3 there. And then keep going. CH2, 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 CH3. Okay, so just make sure I got 6. 1, 2, 3, 4, 5, 6. And then off of the second carbon, there's a 1 carbon branch. So that's my 2-methyl. All right, line structure. The fastest and easiest way, once you get the hang of it. Put your pencil down, and that's 1 carbon. 2, 3, 4, 5, 6. To the 2 position, a 1 carbon branch. And if you counted it backwards and put your branch at the 2 position from the end, that would be the same molecule, just drawn backwards, and that would be okay. All right, we are on D. D is 2-heptyne. Hept is 7. The Y-N-E ending tells you you're talking about an alkyne. Where's the triple bond? At the 2 position. The number tells you. So 7 carbons. 1, 2, 3, 4, 5, 6, 7. Triple bond between the second and third. Be very careful when you go back and add your hydrogen to complete your octet. You need 3 here to complete octet, 0 here. You've got a triple bond and a single bond to that carbon already. 0 here, 2 here, 2 here, 2 here, and 3 here. And again, I'm going to go ahead and leave it like that and not draw in my hydrogen, because I'm getting a little bit, could get a little bit cluttered there if I do that. All right, condensed structure. Starting out with a CH3 and then a C with a triple bond to another C, to another carbon. Okay, so you want to show your double and triple bonds in your condensed structure. Followed by CH2, 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 CH3. CH2, 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 CH3. Okay, 1, 2, 3, 4, 5, 6, 7, and the triple bond is at the second position for 2-heptine. Line structure can be a little bit tricky with an alkyne, so that's why I wanted to make sure and throw a problem like this into this worksheet. Remember that your line structure should show some decent indication of molecular geometry, okay? And the molecular geometry about the carbons that are part of the carbon-carbon triple bond is linear. So we need to show that in our line structure. So put your pencil down for 1, followed by 2. The second carbon is part of the triple bond. So 1, 2, 3 for our triple bond. So we've already got 1, 2, 3. This is our third carbon, which is also part of the triple bond, so it also has a linear geometry. So go straight out from that. Okay, so we've got 1, 2, 3, 4 carbons. Everything after that is a tetrahedral geometry. So you want to zigzag your chain after that. Okay, so again, 1, 2, 3, 4, 5, 6, 7 for our heptine. So I'm going to go ahead and write in the red pen that this bond angle here about this carbon of the carbon-carbon triple bond, it's going to be 180 degrees. Same thing here. So don't forget about that molecular geometry. You want to show that, a good indication of what the molecular geometry really is in your line structures. And that is a little tricky when you're drawing a line structure for an alkyne. All right, last but not least, E, we have 3-ethyl 2-methyl pentane. So right, E here, I think we can just barely squeak it in. Okay, so we've got a pentane for our parent chain. So pent is 5. We know it's an alkane because of the ane ending. There is going to be one branch group at the third position that is 2 carbons long. It's an ethyl. There's going to be a separate branch group at the second position that is only 1 carbon long. It's a methyl. Okay, so 5 carbons in our parent chain. 1, 2, 3, 4, and 5. At the third carbon, our 2 carbon branch. You can go up or down, it doesn't matter. 1, 2. At the second carbon, a 1 carbon branch. It's a methyl. I'll go up with this one, but again, you could go up or down, it doesn't matter, because remember, those single bonds rotate freely, so you don't have to worry about going up or down there. Okay, now go in and saturate everything with hydrogen. So 3 hydrogen here, 3 hydrogen here, 1, 1, 2, 2 here, and 3 here, and 3 on this terminal one as well. Okay, so it actually might look a little better if I go down with that ethyl. Okay, I'm going to go down with it so that people don't think I have a cyclic structure here. All right, condensed. So we're going to do a CH3, let's draw that line down a little lower, a CH3, followed by a CH, followed by another CH, followed by a CH2, and a CH3. Now off of the second carbon, we have a branch, and I'm going to show that bond. I'm going to show the bond to the branch group, a branch to a CH3, and off of the 1, 2, 3, off of the third carbon, we have a branch to an ethyl, so a CH2, CH3. Okay. Line structure, again, fastest and probably the easiest. Once you get the hang of it, put your pencil down for the first carbon. 1, 2, 3, 4, 5. Off of that second carbon, there's a 1 carbon branch, so just draw 1 line out for your 1 carbon, your CH3. And then off of the 1, 2, 3, the third carbon of that pentane chain, there's a 2 carbon branch, so 1. It doesn't matter which way you go, because remember the single bonds rotate freely, so you could go this way or this way. You could go to the left or the right. I'm going to just go to the right for my CH2, CH3. Okay, that completes number 1. Let's erase here and go on to number 2. Okay, number 2. Draw each of the following alkenes and determine which will have both a cis and a trans isomer. For those with a cis and trans version, draw both isomers. A is 1-butene. So for 1-butene, but means 4 carbons, and the 1 tells you that the double bond is between the first and the second carbon. So let's go ahead and draw the carbon-carbon double bond first and show the molecular geometry about that carbon double bond. So each of those carbons is going to have a trigonal planar molecular geometry. So about 120, 120, 120 here. Same thing over here, 120, 120, and 120. So I'm trying to show those 120-degree bond angles. So this is carbon 1, 2, and it doesn't matter if you go up or down at this point because we're not trying to draw a cis or a trans. We're trying to figure out if this molecule has cis and trans. So I'll just go down, okay? And I'll just draw, I'll go ahead and draw in all my hydrogen for these problems. Okay, so here's my 1-butene. Now remember, if you're trying to figure out whether or not an alkene can exist as a cis and a trans isomer, we want to first look at the carbons that are part of the carbon-carbon double bond. So let's look at this first carbon here. You want to compare the 2 substituents on that carbon that is part of the carbon-carbon double bond. Remember that if either carbon that's part of that double bond has the same 2 substituents, then it can't possibly have a cis and a trans isomer. Because that means that even if you break the bond and you flip the position of the 2 substituents, nothing's going to change, right? It's going to be the same molecule. Okay, so what do we have here? For this carbon, we have 2 hydrogens. That means that on this side of the carbon-carbon double bond, the substituents are the same. Doesn't matter that on the other side they're different, that this is a hydrogen and this is a CH2CH3. If one side is the same, then again, you can break that double bond, you can change their position, reform the double bond, and it won't change what the molecule is. The molecule does not have a cis-trans version. So I'm going to write here, no cis-trans. Not for 1-butene. Okay, B, 2-butene. So now we're going to move the position of the double bond to the second position in that 4-carbon chain. So again, start out with your carbon-carbon double bond. Make sure that you're showing the molecular geometry about it. That'll make these problems a lot easier. Okay, so we want to put a carbon here for carbon 1. This is carbon 2. This is carbon 3. And for carbon 4, it doesn't matter if you go up or down because, again, we don't know yet if it has cis-trans. We're trying to determine if it has cis-trans. So I'm just going to go down and I'll go ahead and put in all my hydrogen. Okay, and now we're ready to look at each of the carbons that are part of the double bond and determine if their substituents are the same or different. So looking at this one first, a hydrogen is different than a CH3. So I'm going to write diff. Over here, a hydrogen, again, is different than a CH3. So both sides are different. That means that 2-butene has a cis and a trans isomer. Okay, that means we need to draw both. All right, so let's go back to the black pen. And what I've drawn here if we look through the carbon-carbon double bond, we'll see that the largest two substituents are on the same side of the double bond, making that C-shaped here. This is the cis isomer. So I'm going to write here, in fact, let me write it in blue. This over here is the cis 2-butene. So really all I have to do to finish up this problem is I need to draw the trans 2-butene. So I'll do that over here. So here's my carbon-carbon double bond. I want to go up. I want to put those largest two substituents on the opposite side of the carbon-carbon double bond. That makes it the trans geometry. Okay, so I'll go ahead and add in all of my hydrogen, just to be consistent here. And I'll label it again in blue. Okay, so again, look through the carbon-carbon double bond, and the largest substituents are on opposite sides. Okay, so this is the trans geometry. Trans 2-butene. Okay. So even if we had drawn the trans first, we would still be able to look at these two substituents and say that they are different, and look at these two substituents on this carbon of the carbon-carbon double bond and say that they are different, and we could still determine that, of course, this has both a cis and a trans isomer. All right, let's go on to C, which is 2-methyl-2-pentene. Okay, so pent is 5. There is going to be a double bond at the 2 position and a 1 carbon branch, a methyl, also off of the 2 position. So I again want to show my molecular geometry about that carbon-carbon double bond. If it has cis-trans, you have to show that in order to show the difference between those 2 geometric isomers. So it's good to just start out like this, drawing the molecular geometry, the trigonal planar geometry. All right, so it's 2-pentene, so 1, 2, 3, and it doesn't matter if you go up or down at this point because we don't know, again, if it's cis or trans. So 1, 2, 3, I'll just go down, 4, 5, and then off of the 2 position, so 1, 2, there's a 1 carbon branch, a methyl. I'm going to go ahead and just draw lines to my hydrogen. I'm not going to draw them all in, because it starts to get a little cluttered in these expanded structures when you draw in all these hydrogens. And I think that it'll probably be easier to solve this problem without drawing all of those hydrogen in. All right, so look at this carbon that's part of your carbon-carbon double bond. Compare the 2 substituents on it. This is a CH3 and this is a CH3. So they are the same. This side is different. A hydrogen is different than a CH2CH3. But it doesn't matter because it only takes one side being the same to result in no possibility of the cis-trans isomers. So right here, no cis-trans. Okay. Again, you break that bond, you flip the position, you reform that double bond, you just have the same molecule, not a different molecule. Therefore, you don't need a special, unique name for those 2 different orientations. They are the same. They're both just 2-methyl-2-pentene. All right, let's erase all this and go on to D. Okay, D. 3-methyl-2-pentene. So very similar to the last one, except that that 1 carbon branch is going to be off of the 3rd position, not the 2nd position. So again, show your molecular geometry about the carbon-carbon double bond. The carbon-carbon double bond is at the 2 position, so 1, 2, 3, and again, you can go up or down here. I'm going to go down, 4 and 5. for my 2-pentene, there is a 1 carbon branch at the 3 position. So 1, 2, 3, 1 carbon branch here. And then I'm going to go back in and draw lines to all of my hydrogen. All right. Use the blue pen here. Looking at the first carbon that is part of our carbon-carbon double bond, it is attached to a hydrogen here and a CH3 here. Those are different. Okay. Looking at the second carbon that's part of the carbon-carbon double bond, it's attached to a CH3 versus a CH2, CH3. So again, different. Okay, so this has a cis and a trans isomer. So which one have we drawn already? Well, look through the carbon-carbon double bond. The largest substituents are on the same side of the carbon-carbon double bond. I've drawn them both down. They're on the same side. So this is the cis isomer. This is cis 3-methyl 2-pentene. Okay. So now we just need to draw the trans isomer and we'll be all done with part D. So I'll go back to the black pen for that. So now I'm going to draw my CH2, CH3 pointing up. So notice I kept everything the same until I got here, and then I flipped the position of these two substituents so that the larger group is now on the opposite side of the larger group over here. Okay, trans position, and my CH3 goes down. Okay, so drawing all my hydrogen, I'll just draw lines to my hydrogen again. Okay, so we've got 1, 2, 3, 4, 5. We've got a double bond at the 2 position, so we've got a 2-pentene, 1, 2, 3. We've got a 3-methyl 2-pentene, and now this is the trans geometry. Again, because if you're looking through your double bond, draw a line there. Your largest 2 substituents here are on opposite sides. Okay. So this is trans 3-methyl 2-pentene. Okay, last but not least, E, we have 2-hexene. So hex is 6, the double bond is at the 2 position, so between the 2nd and the 3rd carbon. So indicate your molecular geometry there, and then we've got carbon number 1, carbon number 2, carbon number 3. Again, doesn't matter if you go up or down at this point because we don't know yet if it's cis or trans. So I'll just go down for 4, 5, and it's hex, so I want 6. Okay. I'm going to just draw lines to my hydrogen so it doesn't get too cluttered looking. Okay. And we will analyze now to see if these are the same or different. These are different. One is a hydrogen and one is a CH3. So I'll write diff for different. And these are also different. This is a hydrogen, this is a CH2, CH2, CH3. So these are different. So this has a cis and a trans isomer. Meaning that if we broke that double bond and flipped the position of these 2 substituents here, we would get a different molecule when we reformed that double bond. It has to therefore have a different name. Okay, so I just happen to have drawn here the cis. Notice that they're on the same side here. Our largest 2 groups are on the same side of the double bond. So this is cis 2-hexene. So now we just need to draw the trans 2-hexene, and we will be done with number 2. So I'm going to keep everything the same until I get to the other side of the double bond, and then I'm going to go up with the rest of my chain instead of down. So that when you're looking through the carbon-carbon double bond, you can now see that the largest groups are on the opposite sides. Instead of the same, they are on the opposite sides. So now we have trans 2-hexene. Trans 2-hexene. Okay, so that completes number 2. We're going to go ahead and erase here and go on to number 3. Okay, number 3, circle the names that are not possible by IUPAC nomenclature rules. We've got an A through H, and I went ahead and drew them all up here on the board to make this go a little bit faster. Let's go ahead and try to draw out these molecules in order to help us decide whether or not they are possible names by IUPAC nomenclature. So cis-1-hexene. So we're talking about an alkene, and we're talking about 6 carbons with the double bond at the first. 1, 2, 3, 4, 5, and 6. Okay, so I'll go ahead and draw lines to my hydrogen here. Okay, now because we're putting the double bond at the 1 position, these 2 substituents are both hydrogen. That means they are the same. And remember, when you have the same 2 substituents on either of the carbons that are part of the carbon-carbon double bond, it means that cis-trans isomers will not exist for that molecule. So there is a molecule that is just called 1-hexene. That would be the name for this molecule here. But there is no molecule called cis-1-hexene, and there is no molecule called trans 1-hexene. So you should circle A. Cis-1-hexene is not a possible name by IUPAC nomenclature because the double bond at the 1 position means that you would have the same 2 substituents here, both hydrogen, and so therefore you would have no cis-trans isomers. All right, trans 2-butyne. So here we're talking about an alkyne with 4 carbons with a triple bond between the second and the third. And remember that only alkenes have the potential for cis-trans isomers. Alkynes and alkanes will not. So there is no molecule called trans 2-butyne. Alkynes do not exhibit cis-trans isomers. And that makes sense if you look at this molecule and see that there's only 1 possible substituent for a carbon that's part of a triple bond. Not 2, like there are when you have the double bond. Okay. C, 2,3,4 trimethyl octane. Oct is 8. 1, 2, 3, 4, 5, 6, 7, and 8. It's an alkane, so all single bonds, and then they're indicating in the name a 1 carbon branch of the 2, a 1 carbon branch of the 3, and a 1 carbon branch of the 4, and it doesn't matter if you go up or down with those because single bonds rotate. And I'll just draw lines to all my hydrogen. Okay, so I see no problem with this name. This is a correct name by IUPAC nomenclature. D, 2,3,4 trimethyl butane. So let's draw that one over here. So butane is 4 carbons, 3 and 4. It's an alkane, so all carbon-carbon single bonds. And then the name is implying that there's a branch group off of the 2 position, off of the 3 position, and off of the 4 position. And I'll go ahead and draw my little lines here to my hydrogen. Okay. So I'm hoping that when you look at that structure, you right away notice that the name 2,3,4 trimethyl butane is not possible. The longest chain here would be 1, 2, 3, 4, 5. This would not be a branch group. This would be part of, in fact, let me use a different color here. This would be part of the parent chain. This would be a pentane chain. It would have a 1 carbon branch at the 2 and a 1 carbon branch at the 3 position. So this would be a 2, 3 dimethyl pentane. You would never want to call it, name it as a butane, because 4 carbons is not representing the longest consecutive chain of carbons, which is 5. So let's cross out butane here. That's what's making this wrong. And circle D. D is not possible by IUPAC nomenclature. Putting the methyl at the 4 position of a butane chain turns it into a pentane. All right, 2-methyl 1-butyne. So butyne is 4 carbons with a triple bond at the 1 position. Okay, and then in the name we're indicating a 1 carbon branch at the 2 position. So 1, dun, 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 dun. And I'm hoping that right away you are zooming in on this carbon, which has 1, 2, 3, 4, 5 bonds. Which is too much for a proper octet. So we would not be able to have that 2-methyl branch in that position. We wouldn't have anything that could branch off of this carbon if it's triple bound to this carbon and then singly bound to this carbon. Okay, so circle E. E does not exist. All right, F, 2-methyl 4-ethyl decane. So dec is 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then at the 2 position we have a 1 carbon branch, it's a methyl, and at the 4 position we have a 2 carbon branch. It's an ethyl. So I'll go ahead and indicate lines to my hydrogens. Okay, and I see nothing wrong with this name. This molecule would exist and it would be called 2-methyl 4-ethyl decane. All right, on to G. 1-ethyl heptane. Hept is 7, so 1, 2, 3, 4, 5, 6, and 7. And then we're indicating that off of the first carbon, there's a 2 carbon, F, 2 carbon branch. So 1, 2. Now I'll go ahead and indicate all my hydrogen. Okay, so I'm hoping that right away you'll look at this and say, that's not possible, because the longest consecutive chain of carbons would not be 7. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be a nonane chain. It's not a heptane. So let's circle G as being not possible. You can't have a branch group off of the very first position, because then it just becomes part of your longest consecutive chain. You also can't have a branched group off of your last carbon in a chain, because again, then it becomes part of your longest consecutive chain and changes what your parent chain is. All right, last but not least, 1-octyne. Oct is 8. 1, 2, 3, 4, 5, 6, 7, and 8. And there's a triple bond at the 1 position. Add in my hydrogen for octet. And this molecule would exist and would be called 1-octyne. So don't circle that one. It is correct. All right, let's go ahead and erase here and go on to our final problem, which is number 4. Okay, problem number 4. We are going to be providing the name for these 4 different molecules that I have drawn up here on the board. Starting over here, we have 1, 2, 3. 3 carbons. That would be the prop prefix. Notice there is a triple bond, so it is an alkyne, so we want to use the YNE ending. Our final answer here is propyne. Now we don't need to specify the location of the triple bond because there are 3 or fewer carbons in the molecule. So we don't run into those different positions for the triple bond until we get to 4 or more carbons. All right, moving on to the second one. This is a line structure. We have 1, 2, 3, 4, 5 carbons. Remember, all of those points represent a carbon. They're all carbon-carbon single bonds. So we have a pentane, but it's connected in a cyclic ring structure. So we need to add the prefix cyclo to come up with our final answer, cyclopentane. Okay, moving on to the third, another line structure. You want to definitely get familiar with seeing molecules drawn in line structure. We have 1, 2, 3, 4, and again 5 carbons for another pent. But this is a pentene. Notice there is a double bond. That makes it an alkene. Where is the double bond? There are more than 3 carbons, so we definitely want to specify the location with a number. It begins at the second carbon. You can double check by counting backwards, 1, 2, 3. The 3 position would be too high, so we definitely want to count this one forward. So we have a 2-pentene, and anytime you have an alkene, make sure that you double check for cis-trans isomers. In this case, this first carbon of the carbon-carbon double bond has a CH3 as one of its substituents and a hydrogen. Remember, in a line structure, we don't draw in the hydrogen, they are just assumed. So if you need to convert this into an expanded structure to see that there is a hydrogen there, you should do so and prove that to yourself. Okay, so there's a hydrogen here and a CH3. So on this side of the carbon-carbon double bond, the substituents are different. On the other side of the carbon-carbon double bond at position 3 here, we have a CH2CH3, and we're comparing that again to the other substituent, which is a hydrogen. So again, different substituents on this side as well. When both sides have different substituents, it means that there are cis-trans isomers. So what do we have here? Look through the double bond. Our largest 2 substituents are on opposite sides of that double bond. So this is trans 2-pentene. Okay, last but not least, we have 1, 2, 3 carbons. So another prop, but this time we have a double bond. So it is a propene. Again, we only have 3 carbons. When there are 3 or fewer, you don't have to specify the location of that double bond because there's only one place it could be. So imagine the double bond was over here instead, it would still be on the first carbon of the molecule. It would just be drawn backwards. Okay, so we're going to call this propene, and we don't need the number there. Now cis-trans, anytime you have an alkene, it's a good idea to just double check for that. Look at your first carbon of the carbon-carbon double bond. It's got the same 2 substituents, a hydrogen and a hydrogen. So that means that this molecule cannot exhibit cis-trans isomers. If we broke the bond and rotated the position of those 2 hydrogens and reconnected the double bond, the molecule would be identical. It would be unchanged. So we don't need a special name determining if it's cis or trans. All right, so this will conclude our problem set 16, and I hope that you will consider tuning in to tutorial number 17. Thank you very much.